So, as I was saying, I spent all weekend thinking about this, and all I could come up was the title. But I think it really captures what I like to explain. The point of view was made much easier to develop, I think, by Kapustin's ideas on Rozansky-Witten theory. So what I'm going to describe now, it's really a reformulation of his idea, is a global interpretation of the matrix factorization categories. And this story will turn out to be consistent with the construction of toric mirrors by JT quotient by fixed point categories. And specifically, the interpretation of fixed point categories, I mentioned last time, is the fibers of a map, in this case the dual torus. And later we'll see an analog for non-abelian groups, actually later today. It will also be compatible, will bring in, would bring in, actually I'm saying, reading the sentence backwards, would bring in a beautiful description of the equivariant homology of the based loop group of G, which is due to Bezrukavnikov, Finkelberg, Merkovich, and that's what brings in the Langlands dual group. And it can be then justified by an independent fixed point construction of categories called the curved Cartan complex, and that I'll discuss next time. So if you want the one-sentence summary, actually I'm giving you two one-sentence summaries for this story. The first one is that the trivial A-model gauge three-dimensional topological quantum field theory is the Rozansky-Witten theory of the Bezrukavnikov, Merkovich, Finkelberg cotangent bundle, blown up cotangent bundle of conjugacy classes in the Langlands dual group. Of course, a lot of the content is packaged in the last construction. I'm not entirely sure what this means, because I'm not entirely sure I understand how to gauge actions on tensor categories. But one interpretation of this is spelling it out object by object, and that's more precise, and that's what I'll try to make precise. Exhibiting a local A-type action A on a category C, of G of a group on the category C, is the same as exhibiting C as an object in the Kapustin-Rozansky-Witten 2 category for that cotangent bundle, which is a holomorphic symplectic manifold. So the data for the group action that we want will be captured by making the category into an object in there. That's what the story is about.
Sorry, what did you say BFM stood for?
Bezrukavnikov, Finkelberg, Merkovich, and they give a specific blow-up of this space. That will be, I'll describe it at the very end, but okay, probably it's impossible to ask question based on this level of vagueness, so maybe I should just proceed.
Oh, sorry, is there also something called a B-model gauge three-dimensional TQS?
There could be, yes. I didn't think hard about that, but yes, if you're going to ask, do I have a picture for that? The answer, I have one that works fabulously for a torus, and the one that works badly for a non-abelian group. So I don't know how to fix it for a non-abelian group, how to fix the B to A story for a non-abelian group yet. There's a reason for that. If at the end, if we have time, I can explain more. But yes, there should be a symmetry of this sort, that A model for group action should correspond to something associated with this manifold. The B-type group action should correspond to something else. And for a torus there is. It's something like a Fourier-Mukai Cartier transform in that case. All right, so let's recall the problem was, which is independent of group actions and categories and gauging stuff. It has to do with curved algebras, with matrix factorization categories. So X is a smooth affine variety. W is a function, holomorphic function, algebraic, with isolated critical points, let's say. And we define the matrix factorization category to be the sum over all critical points of the matrix factorization at the critical point for the shifted potential, making it vanish at the respective critical point. And once you've done that, at each critical point, you define this to be a differential grade category whose objects are pairs of projective of vector bundles, projective modules defined nearby, and maps between them P and Q with the property they compose to multiplication by W in both directions. So it's a two-periodic curved complex, if you want. So two things are happening. The differential doesn't square to 0 and the grading is collapse mode 2, and both things are important. But if you take a hom between two such things, that's actually a complex. So this ends up being a differential graded category. You can define the derived category as this mod homotopy is. It has a nice structure of a triangulated category, if you like triangulated categories at least. Orlov gave a nice description in terms of categories of coherent sheaves on the fiber, the coherent sheaves on the critical fiber modulo perfect complexes. But in particular, it's more obvious from a second description, this category is supported at a critical point C, at the critical values of, and particularly at the critical values, the critical points. My mistake. Notice that you can tensor an object in here with a vector bundle on X. So this is a priori almost a module category over the category of coherent sheaves. So it's an all linear category. So you can localize it on X. And when you do that, if you decide to pass to the open set where W has no critical points, you'll get 0. Now the mirror construction for toric varieties would be explained, and many other things actually, would be explained naturally from the assumption that if you restrict this matrix factorization category to a, let's say, a smooth subscheme Y, you get the matrix factorization category for the potential restricted to Y. That's what you would need to, and everything would fall into place. You also need it somehow internally. There's a place internally in the theory of curved algebras where this kind of, this statement pops up as a natural statement. Restricting the category of matrix factorization to a submanifold produces a matrix factorization for the restricted potential. But there's a way to compute the restriction inside the category of matrix factorization which does produce that. But this is impossible, literally. It's impossible because, for instance, you could take an example where W has no critical point along Y. Therefore, the support of the category is completely disjoint from Y. But the restriction of W to Y has critical points. But because of the first thing, the actual restriction of the category gives 0, whereas the potential on Y would give an interesting category. And Kapustin's goggles, I'm explaining now, was going to fix that.
Why would the mirror construction follow from this assumption?
Well, I could cite page 9 of the lecture last week, but there is a construction of the mirror for the GIT quotient in terms of, I could just repeat very colorfully, I guess. I could repeat very colorfully, no white chalk. What I said last time, that if T acts A-type on, say, a category C, that is the same as C is a module category over coherent sheaves on the dual torus. So in particular, if C is a Fukaya category of X, then the mirror of, then what this tells you, the mirror of X comes with a holomorphic map to T check. Holomorphic. And the fixed point category is going to be the fiber over 1. And now every mirror of a toric variety can be written as a GIT quotient of some large complex vector space by some torus. And the mirror of I'm sorry, let's try again. Every toric variety and the mirror of Cn, well, one candidate for it is just is GL1 to the power n with potential the sum of the coordinates. So from this plus that, you actually recover a combinatorial recipe for constructing the mirror of a toric variety, and it is a standard Hori-Vafa-Giventhal improved by others later. So I'm sorry I did not a bit hard to. Should I take this down for 1 sec? Don't know how to do that though. Are you taking responsibility for the consequences? Okay. All right. So, I mean, this is not how Horry, Waff, and Giventhal said it in terms of fixed point categories, but that's what they wrote it as a recipe. And they could be justified by saying that, well, I mean, when you compute it, what you're just going to do is just restrict the potential to the fibers of the map. So this will map to some smaller torus. So I didn't finish the sentence. So this leads to a map from GL1 to the N to some T check. That's not the torus of the toric thing, so maybe it's some S check, and the fiber with potential with summation of Zi is a toric mirror. Okay. I don't know why I didn't write it here, come to think of it. But the problem is there is no, in this picture, in this view of matrix factorization, there's simply no legal way to define this operation of restriction to give the answer you want. So that's what Kapustin's idea fixes. So to explain the picture, I mean, the picture involves a sheaf of two categories, which I'm sure will make Sean very happy. So, so I think to make it understandable, I mean, because the idea is already understandable one level down, we'll just stick with categories and schemes and modules, all right? So, but let's stay a bit abstract at first, because that's how you can generalize it. So let's see be a category. It could be the category of coherent sheaves on a smooth variety, a linear category. And let's assume it's a complicated category, whatever that means. But let's say you know an easy object inside. And let's try to understand C by localizing at A. And what this means is you replace an object in C by the space of maps hom of AX. And this space is actually a module over the endomorphism of A. I think they act on the right. I'm always confused by them. And the morphism from X to Y, of course, induces the module map from hom AX to hom AY. And this way you map the category C into modules over the ring A, which are, if A was an easy object, maybe you can understand that. If this map, if this functor from C to modules detects isomorphisms correctly, then A is called the generator of the category. And then if C is abelian with some technical condition, and in fact you can prove that C was the category of A module, so in that case you've lost nothing. You really remember the entire category. But let's assume we're not in this happy situation, so there's lots of information here. And then you try to get to a different part of the category by localizing a different object B and looking at the category of end of B modules. Different algebra. And of course you want to patch them together to recover the category. And there's a natural place where all these charts for the category live. And that's a spectrum of the Hochschild cohomology of C. And as by its nature, this is a symplectic manifold, a symplectic form of degree 1, the supermanifold. If C in the previous case, where C was coherent sheaves of a smooth variety, this will be the algebra of polyvector fields over that variety. So it has an odd part. Algebraically, it's a 1 Gerstenhaber algebra. It's a differential grade algebra with a Poisson bracket of degree -1. Does it say here? No. Poisson bracket. And this -1 is the 1 on the left. And now for each object A, the endomorphism algebra of A turns out to be an algebra over this Hochschild cohomology algebra. This Hochschild cohomology algebra is commutative, is minimally commutative. For people who know that, it's an E2 algebra, and end of A will be an algebra over this E2, codimension 1 algebra over this E2 algebra. It has just enough commutation. And this is a more geometric thing because it's already commutative, so you can try. In nice case, it's really geometric, but you can always try to pretend it is, at least. And this algebra is supported on a coisotropic locus. For example, if the object A was the structure sheaf itself, then end of A was just a structure sheaf as an algebra, a sheaf of algebras, and its support would be a zero section in the odd cotangent bundle. I'd even like to think that it's Lagrangian, the support, but I don't know how to say that in general, because if you assume nothing, then this guy could be a very ugly space, and I don't know what half-dimensional means. But the coisotropic property you can formulate algebraically easily, and this follows from general nonsense. And if you're in a very lucky situation, you might find, if you just look at end A and this Hochschild cohomology, that's in some sense a local chart on the Hochschild cohomology of the entire category. It's not so atypical, but it requires a bit of luck. I mean, it's a kind of what you'd like to expect. So this gives a model, an attempted model for a global object C which you don't understand from its local charts by patching over the Hochschild cohomology spectrum. That is the idea we're going for. So here's the picture. Does it fit? Maybe. Okay. Without the title, it fits. All right. So here down there, this blue thing, this blue circle, maybe this big blue thing, is the spectrum of the Hochschild cohomology of the category, and you want to think that the category lives over it. And specifically how? If you have an object A, where it lands inside Lagrangian, which lives in an open chart, which is a spec of its Hochschild cohomology of the endomorphism ring, an open chart in the spectrum of the Hochschild cohomology of C. If you have some other B, it lives over some other pink Lagrangian here with another chart, which they overlap, and hom of AB, the space, actually is supported on the intersection of A and B, right here. And here you begin to see the phenomenon that's going to solve the puzzle about curved algebras. Let's say we had some other object C supported somewhere here, say, this chart. You can see as far as you see, as far as A can see, B and C are disjoint. B is here, C is there. But of course, in the category, B and C do intersect. So in the category as a home, it's completely missed by localization, I think. So what the puzzle we're trying to explain is actually a very simple thing, or could have a very simple solution, and it does. We're looking for the home in the wrong place. We're looking in the neighborhood of a variety which just doesn't see it, doesn't see the intersection. The other thing worth noting is the double vision caused by these goggles. If you say, let's forget about the category and let's try to compute everything from this projection here, this is what you see through the goggles, then you're computing double. So for example, if we're computing if the tensor product of this Lagrangian end B with end A over the ambient Hochschild cohomology, you get, under some mild finalist condition, you get the double of the home space. You get the endomorphism algebra of hom of AB. Instead of computing hom, you're computing the end of hom. And that actually is because this picture should be interpreted as a character. And the character always has this doubling feature. The simplest case, a character of a group representation. Take a finite group. Its character is a function, a class function on the group. Take two representations, you get two functions. The only reasonable meaning of hom between two functions in a vector space are inner product. If you have one, you do have one in this case. So you compute the inner product of the two characters. And what do you get? You get the dimension of the space of intertwiners. The dimension of a vector space is its Hochschild homology, the simplest case. So that's what I mean by doubling. Hochschild homology or cohomology is actually better here. So character always has this doubling feature. Doubling in the sense it's some form of Hochschild homology or cohomology. That's what happens here too. So if you forget what was up here and just see the projection, you're always computing in some sense a double of what you wanted. Very general principle. So as an aside, actually,
in your example with finite groups, you get Hom between the two representations.
you get the inner product of two characters is the dimension of the space of dimension of a Hom.
But it's not the dimension of end of the Hom.
No, but the dimension is the double. The dimension of a vector space, the Hochschild homology.
Oh, dimension in that sense.
Well, dimension in the only sense. I mean, it's not obvious. You don't recognize it in this very low categorical example because when you say the dimension of a vector space, it doesn't look like a double,
Yes.
but it is if you.
No, I don't see it. How is it a double?
It's a Hochschild homology. Okay, so the Hochschild homology of, if you have the algebra, say k of x, the Hochschild homology of this algebra, I could take cohomology, was going to be differentials on x, so k of x and dx. So adding a generator for the even generator. It happens to be an odd generator. If you have a vector, and I should put a 1 here. If you have a vector space V, the Hochschild homology of V, defined by an abstract categorical definition, is a dimension of V. So this is a double, so this Hochschild homology is also what I call a double. And from here on, at every higher categorical level, Hochschild homology does perform a very visible doubling. So for algebra, it doubles the number of generators. But here it's so low down, you cannot read it in this way. I mean, I could write it in a formal way, which makes it look like it's a tensor product of V with itself, but it probably wouldn't be enlightening.
Or just a representation of a group. I mean, that its character is something that lives on G mod G. So it has that doubling, it has G twice. It has G mod G, which you
yes, if you like, yes, if you like to say. I mean, it's doubling at that level. Doubling actually makes things smaller instead of larger. It's modding out because there's no derived. Somehow, it's this is in degree 1 for Hochschild homology. It's a derived feature that causes a doubling. But you're so low down, there's no derived parts. You're missing. You fail to see the enlargement. It doesn't get larger. But that's because you're so low down, you don't have derived functors somehow. That's why it looks like it's not a doubling. But the operation which produces a dimension of a vector space is completely analogous by an abstract definition to that which gives a Hochschild homology of an algebra. So,
Is there an intuitive reason why I should expect this thing to localize over the Hochschild cohomology, spec of the Hochschild cohomology?
because an algebra is an algebra over its Hochschild cohomology, which is more commutative than it is. Hochschild cohomology is a center, yes, a derived center. Yeah, maybe that's it. That's a short answer. An algebra localized over its center. That's a picture. But then Sean will complain that he doesn't see how a center is a double. But it is. So, I mean, at the level we actually want to go, at this level of categories already, you are computing. If you can do this computation. I mean, if you take a commutative, a nice smooth variety, these things you can compute, and you actually will see the thing doubling. But I'm trying to address a bit more systematically this if I have time. Let's see.
It's going from the space to a cotangent bubble, and this picture is a cotangent bubble.
That is correct. That's a doubling as well, yes. But for V, there's no underlying space, so again, that doesn't allow you to do that construction. For vectors, there's no spec of a vector space anymore. All right, so let me try to run through Hochschild homologies and cohomologies and their cohomologies and their meaning a little bit to bring some order. So an object of categorical depth k has a succession of k plus 1 Hochschild cohomologies ranging in categorical depth from k to 0, but which have an additional algebra structure of commutativity ranging from 0 to k. So E1 to ek plus 1 algebra objects. So just to pin things down, actually here's the example. A vector space, I think it has categorical level 0. Just accept that, we have to start somewhere. And it has a zeroth Hochschild cohomology, which is the endomorphism of that vector space. And it would have a minus. I'm worried I got my gradings wrong now. It would have a -1 Hochschild cohomology, which is its dimension in this case. I've left this one out. Even though I mentioned it before, my mistake. Because it's a confusing one, I find. But it's zeroth Hochschild cohomology is the endomorphism algebra, and that's an algebra, an associative algebra, that's all there is. By its nature, actually, you have to be careful, it's a vector space. It has a multiplication, and because of that, it has a category of modules, so you can cook up a category from it. But by its nature, it's a very well-defined vector space. And Hochschild cohomologies are always endomorphism algebra, but in a different world. So for an algebra, its zeroth Hochschild cohomology would be the algebra of a tensor A op, so the category of AA bimodules. That's a category, and it has a composition. So it's a tensor category. This is a category of endofunctors of the category of A modules. So it's an algebra. It's a category, but it's an algebra because you can compose. Now the tensor category, it has an identity object, which is the bimodule A, as a bimodule over itself. And its endomorphism algebra is now an E2 vector space, a vector space with a commutative multiplication, which can be computed in a derived world as X over A tensor A op of AA. So this is the identity, and we're computing endomorphism of the identity. And that's the ordinary Hochschild cohomology of the algebra. And it is, by its nature, a vector space, but it has a multiplication which, moreover, is commutative. It has a multiplication because it's an endomorphism ring of some object in a category, and the commutativity comes from the fact that the category itself had a multiplication. And this goes on. So if you have a 2 algebra or a 2 category, as categorical level 2, the zeroth HH star would be functors from the category to itself, endofunctors of the category. It's a 2 category by its nature because it's a category of functors between 2 categories, but it has a composition law, so it's an E1 2 category. If you take the identity object inside and you take its endomorphism algebra, it gives you an E2 category, and if you repeat, you get an E3 vector space, an algebra which is once more commutative than minimally required. It's actually an in characteristic 0, EN algebras are easy to describe. The differential grade algebra of the Poisson bracket of various degrees given by the index. So an E1 algebra is an algebra, it's not commutative and has a commutator bracket. And the condition that the bracket is equal to the commutator. An E2 algebra is going to be commutative and has a Poisson bracket for the multiplication and has degree -1. It's kind of the commutator vanishes, but behind it, lower down, there is something that doesn't vanish, and so on. That's a theorem, not a definition, by the way, and it's characteristic 0. And I think I was going to spell out this, let's see if I wrote it correctly, this example of 2 algebra. If A is a commutative algebra, then A is an algebra over itself, and as such it represents the identity functor between the tensor categories on the tensor category of A modules. Its first Hochschild cohomology is going to be the category of modules over the Hochschild homology I wrote here. And I mean, I could have written A op, and I probably should have done that, I have a feeling. Doesn't seem to matter, but I think it does. And the second Hochschild cohomology is going to be the endomorphism of the identity functor in the category of modules over this guy. So you compute it as X over A tensor A over A tensor A op of AA, so you can begin to see the pattern. It's repetitive, taking the endomorphism of the identities actually continues. So this is roughly how things run, I mean, just to give an idea, and there's a meaning to them that's very important. Still partly conjectural. I have a point of Hochschild cohomologies, and for us the only point that might be relevant is deformation theory, namely the top Hochschild cohomology that you can define. Go as high as you can, and at that level you get something which controls the deformation, obstruction, automorphism theory via the Morey-Cartan equation. D gamma plus 1/2 gamma bracket gamma is 0. So in other words, elements or formal objects gamma in the kth Hochschild cohomology satisfying this equation are going to give you the formal deformation space of the original object.
And which one was the top again? The top the one that was the most commutative?
The top was the one that's as far as you can go. So this is the bottom, this is the top. So it's in the case of algebras, it's the most commutative one. It's a vector space, the most commutative one. It's always a vector space. When you reach vector space, a very commutative, you stop. And the bracket in here will have increasing degrees as you increase k. So the funny thing that happens is that the degree in which you find the deformation space goes up with the categorical level. So, for example, for K0, which are vector spaces, we're saying that the endomorphism algebra of a vector space is the endomorphism deformation obstruction theory of a vector space. Let's see. Actually, I have written the example, so let's get to that. For a vector space, it doesn't sound like there are many deformations, but if you make it into a complex, of course, there are deformations. So the Hochschild cohomology, the top one, is the endomorphism algebra. And infinitesimal deformations are things you can add to the differential. That's about the only thing you can deform. So at degree 1 maps, but there's a condition, when you're serious about it, a differential should square to 0. So d plus gamma squared is 0, and that gives you the Morey-Cartan equation. When k is 1, you can start with actually start even with an algebra, if you want. Then cochains for the first Hochschild cohomology are maps from A squared to A. That's a bar complex for Hochschild cohomology. Maps of degree 0. Let's just assume it's an algebra now. And the Morey-Cartan equation turns out to be equivalent to saying that the original multiplication m, I should say that. So m is the original, plus the new multiplication mu is a new associative multiplication. So that's the associativity condition of the new multiplication. So here deformation, these maps are things you can add to the multiplication. If it was really a DGA, then in fact the 1HH2 would contain a lot of maps which would be the A infinity deformations of A. For example, you could have a degree 1 map from A to A, which you could add to the differential, and lots of other MPs. So for the DG story already takes you to A infinity algebras right away if you want to make this statement precise. So for K is 1, it's already a classical fact. I wouldn't even know the first person to credit with this is. Certainly Kontsevich popularized it, but I think it goes back probably to the original work of Gerstenhaber and Hochschild. For a certain class of K categories, for those coming from EK algebras, John Francis has a very general theorem. I think in arbitrary characteristic, even homotopical. But for general K categories, maybe Lurie's work of derived algebraic geometry will set it up. But I think it's still something we believe, but it has to be set up. But that's the point. If you like, the top Hochschild cohomology controls deformation. That's why it's the thing you want. And the other ones, you need to get the top to compute the top. At least in theory. How are we doing? Remarkably well. Any questions? It's a little too vague, I realize, to ask questions, but
Sorry, the top in that sense was there were two indices. One was the categorical depth of the
yeah, you go as
homology, the other is the degree.
you start by computing the end in the world you live in, and you keep taking the identity functors and compute end until you run out of identity functors because there are no more categories. That's the top. It's a vector space with a very commutative multiplication. Sorry?
And all degrees of the Hochschild cohomology at that point. Isn't there a degree in the Hochschild cohomology?
Yes. Yes. Sorry. What was the question about degrees, though?
what controls the deformation?
Well, there's if you want, very good point. Thank you. Yes, that's very important. If you're insisting on preserving a Z grading, then you have a specific degrees like HH2 for algebras. If you're allowing the collapse mode 2, you have a parity, but parity constraint. But even then, the mode 2 story leads into, I think, fine question. Depending how you phrase the question, the statement can be easily true or false. I don't think we understand derived mode 2 homological or homotopical algebra well enough, but that's what's supposed to happen. So the even Hochschild homology of a category controls its deformation theory.
From a field theory point of view, can you say that this tower is just what you attach to various spheres?
Yes, if you have enough duality. If you have enough duality so that Hom can be rewritten as a tensor product, so you can write as a tensor the dual, then these are the things that are very good. These are the things that attach to the various spheres. So the 0 sphere you attach 0 Hochschild cohomology, the 1 sphere you attach 1 Hochschild cohomology, and so forth. So don't know, can I draw a picture? That's a bit convincing. What you really attach to, let's look at, say, dimension 2. What you really what the Hochschild cohomology corresponds to is more like something like this. Algebraic geometers should love that. Or something like this. It's like a disk with a doubled origin, or two disks glued along an annulus. This is, sorry, it would be the 2 Hochschild cohomology. And if you're lucky, you can replace it by an actual sphere. So this would be actually 1 HH star, the way I wrote it, because it's a line. I'm sorry. I shouldn't improvise. So this is a line with doubled origin, or 2 intervals attached along some segments of their boundary. And of course, up to homotopy, they're the same as the circle. And indeed, if there's enough duality in your theory so you can compute a Hom by tensoring with a dual, then you can get the computation for this object by computing this object with, I think for people who know that, with this bounding framing. So the sphere with a bounding framing. So maybe I can, why can't I write that here? So if there is enough duality, is present in the category, I think you need K plus, let's make this P plus 1 duality in this case. Then PHH star is computed is let's say the path integral of the P sphere with a bounding framing, with the framing bounding the P plus 1 disk that's in the HH, in the TQFT generated by the original object, by the original K category. What it always is, I was trying to say, is something like this, which I want to think of as a band-aid. It has a sticky side you can slap onto something, and a pink side where you can write "Mom loves you" or something. And because it's an operator, it's end from something of something. So if you have some other manifold here, you could slap it on and change the result of the path integral of the manifold by reading what comes out, reading "Mom loves you" now here on this side. And this is in fact the physicist's perspective of deformation. Deformations are given by fields in a TQFT. You insert a local field at some point inside your manifold and integrate over the manifold. And that's why deformations are given by this guy is an appropriate dimension. If you want to deform the original object, you want to deform the entire category, you need to do this thing for the top dimensional manifold. That's why you need a top Hochschild cohomology. So if you've seen this picture of deformations constructed from a certain field, it's helpful. If not, it's probably confusing. Okay, let's try to run over the Kapustin's two-categorical picture. And let's try not run out of time. So we're going to have the same story as before in the category. We're going to take objects, localize that objects, and spread that over the Hochschild cohomology, except we're going to look at the top Hochschild cohomology. Its spec is now going to be a symplectic manifold with degree 2 symplectic form, so it's even, so collapsed mod 2, it's a symplectic manifold. And instead of endomorphism of the object, we're going to take the first Hochschild cohomology, which are going to be the endomorphism of the identity in end of A. End of A is now a tensor category, because this was a two category. And here's an example. And here's a mistake. I knew it was there, but I couldn't find it earlier. All right, start with a complex manifold. And let's see, be the two category of OX linear categories. Maybe I should say sheaves. The sheaf of two categories should locally give you all OX linear categories or module categories over the category of coherent sheaves. So because X is a commutative thing, O has the category of all modules as a tensor product. It's a tensor category. You can talk about module categories over it. I'll give you a two category. So its second Hochschild cohomology, the spectrum of that turns out to be the cotangent bundle of X with fiber of degree, I think, -2. I'm always confused, 2 or -2. I think it's -2. And I should really put a hat because it's the formal neighborhood of a zero section that you read off in principle. Of course, if in the ordinary world the fiber is being graded, there's a cone action along the fiber, so it doesn't really matter whether you complete or not, because the grading tells you exactly how to break things up. But of course, already here you see that something will change dramatically if you collapse the grading mod 2. Because at that point, we're dealing with a huge manifold, and we're only seeing a little piece of it before, the zero section. Okay, so let the object, I want an object here, let it be the category, just the category of coherent sheaves of X, on X itself, if you like. It's a bit like taking the algebra inside the category of as a module over itself. Its first Hochschild cohomology is going to be OX, and it sits on the zero section, because it's X in the category of OX modules of OX with OX. And it will sit on the zero section of the cotangent bundle. Let's take another example. Let's take the category, which is a category is just the vector spaces. Whereas a module category is, what it does is take the fiber at X. So when you tensor a vector space with a sheaf on X, by definition I'm declaring what you do, you're tensoring with a fiber at X, and it should be a derived fiber actually. If it's a vector bundle, just tensor with the fiber of that bundle. So that makes vect into a module category, therefore into an object of these two categories. So the first Hochschild cohomology is going to be X over, where does lambda Tx come from? Oh, because the zero Hochschild cohomology. X over lambda Tx of C with C. And that's a symmetric algebra on Tx. And these are the functions of the fiber T star X. So the support of the first Hochschild cohomology is going to be a Lagrangian again, but it's a vertical fiber of the cotangent bundle at X. So you have to go to the calculation, zeroth Hochschild cohomology, first Hochschild cohomology to arrive at that. And finally, I mean, that's the example which I think Kapustin essentially gave, and was his starting point possibly, or was a key ingredient at least. Let C be the category of matrix factorizations of X with a potential W. And in that case, you can compute that the first Hochschild cohomology is going to be supported on the graph of a differential of W, of course, as the formal germ of that, the zero section. And if you compute the Hom interpreted correctly, which is not as X but as Tor of OX opposite with O, if you compute the Hom in this Kapustin projection of the structure sheaf, what we have from the structure sheaf, and what we have from matrix factorization, well, it's just the intersection of zero section, something coming in like that. What you get is the Milnor ring of the potential W. It's I'm assuming isolated singularities here, just to make life easy. That's an easy homological algebra computation. And that turns out to be the Hochschild cohomology of the category of matrix factorization. That's a doubling. Again, that happens. If you compute Hom inside the original category, Hom of the generator with the category of matrix factorization is this category of matrix factorization. Hom from, so I should say, so if A is an algebra and we're looking at A modules, Hom over A of A into M is M. Very basic fact. So here OX was the algebra, we're looking at modules over it, we view this as a module over it. Hom computed inside this two category gives you the category of matrix factorization itself. But Hom of their characters, of their shadows, computes the Hochschild homology, the double.
Okay, see that last line?
It's a doubling coming from the character. I'm sorry for the joke. It was very late last night when I wrote that. So Kapustin conjectured that any holomorphic symplectic manifold should carry, sorry?
Does Kapustin mean Kapustin-Rosansky?
In this particular sentence, you mean?
Yeah.
I don't know. I've heard lectures. I'm not sure. I never looked at the paper, if you were asking, but I've heard lectures by Kapustin. Particularly his ICM talk is what I had in mind, but maybe it is the joint work with Rosansky. In that case, I apologize. Conjecture that, to Rosansky obviously, conjecture that any holomorphic symplectic manifold should carry a natural sheaf of those should have in two categories, shouldn't they? Two categories, of which the manifold itself is the second Hochschild cohomology, is this Kapustin-Gogol projection, but in the Z2 graded world. He also posited that there are objects, canonical objects, associated with smooth Lagrangians inside Y, and when they intersect nicely, you could tell what the Homs are supposed to be. So here's a proposed implementation of that construction. I call it the categorification of Y, but it could also be called the Shukrut-Garni of Y, and Y itself the Shukrut. So it's almost a definition minus a missing theorem. The germ of CG of Y near any smooth Lagrangian, near a piece of any smooth Lagrangian L inside Y, is a two-category of OL linear categories that we studied before. After you identify a neighborhood of L in Weinstein coordinates with a cotangent bundle of L, you just put in the two category of module categories over the category of tensor category of coherent sheaves on L, or the two category of OL linear categories. So that does require a choice of Darboux coordinates matched with L to pin that down. And formally, what's easy to check in formal deformation theory is the consistent definition. It appears problematic because instead of telling you what the category is on an open set, I'm telling you to explain what it is, I must choose a Lagrangian like this. And of course, if somebody could choose a different Lagrangian like that, and it better match the two categories together near this point. And formally that's true, meaning Hamiltonian movements of L can be lifted to this sheaf of two categories. So you can patch, in other words, you can patch charts if you like, or it doesn't matter how you choose your Lagrangian germ. But unfortunately, this is only in formal deformation theory, which means the formal neighborhood of the point of the Lagrangian. So you can only match these two things in the formal neighborhood of their intersection, and of course you need to produce a sheaf, so one needs to make this convergent. So what is needed? A convergent deformation theory to go with what we know. And then you need some finiteness or some notion of coherence for the categories, for the objects in the two category, so that operations on them live not just at a single point, but on a small open set near the point. So that's the only way we're going to patch things together. I should also say I'm a bit skeptical that the...
What do you mean by the Hamiltonian motions that this sheet?
Well, I mean, if you move this Lagrangian to that Lagrangian, I'd like to be able to say that you can identify the category of all linear categories on one with the category of all linear categories on the other, because that is meant to be associated to the open set, not to the open set with the choice of Lagrangian. That's what you're supposed to. So you have to remove the additional choices. And of course, the additional choices are obtained by Hamiltonian motions, are related by Hamiltonian motions, so you have to be able to mod out by those. And formally in deformation theory, it checks out.
Well, then you were saying that given an open around the Lagrangian, define it by the Lagrangian, and just...
Well, I'm saying, well, yeah, what's the category near this point? I'm telling you this. Choose the Lagrangian germ and identify the neighborhood with the cotangent bundle, and now the category is the category of OX linear OL linear categories.
Oh.
That's what. But of course, you could make different choices, and then you have to be able to say that they're naturally identified if you naturally identify the choices. So that's a flow.
More things you could check than just this Hamiltonian.
There might be
More things you could check.
no, I think infinitesimally that's all you need to check. I mean, I didn't write any of it down, so there's always a possibility of a surprise. But
About taking like a Fourier transform, rotating the Lagrangian.
you can rotate the Lagrangian by Hamiltonian motion.
Well, you need to check the connection is integral. I mean, you have,
Yes.
there's a connection.
Yes, and it's flat. It's right. It's
It's flat, but you also need to check the...
Right, that's exactly right. That's a part you cannot. So all we have right now is formal deformation theory. So what we can check is exactly the connection, which is flat, and you're good. But what you need to check is that actually, yes, you can actually flow the category around, or at least for any object in the category, you can move it a little bit. It's not going to be true that you can flow the entire category, flow. But perhaps the model is a definition of a coherent analytic sheaf. If you open the book coming from algebraic geometry and read the definition of a coherent analytic sheaf, there are more words in there than you would have thought. And there's a reason for them. The reason is that you have to make the set smaller for some things to work. Choose your object, do some operations, you may have to shrink the set. And that's going to happen here too. We're going to match these things, we're going to be able to move object, move morphism, and so on. That's the expectation of what it should look like. Or that's the only thing I imagine working. I have no idea how I would define this in the algebraic setting, actually. This is not going to work. This is holomorphic construction, for example. No. Well, because algebraically, algebraic symplectic manifolds don't look locally the same, whereas holomorphic symplectic manifolds do. That's the point, yeah. So incidentally, this definition also shows that if you have a Lagrangian, and well, actually, there's a bit of information needed. You need to know the neighborhood as a cotangent bundle. Then there's a canonical a smooth Lagrangian. There's a canonical object in the two categories associated to that. But if you have a singular Lagrangian, then you're in trouble. You don't know how to lift it to the category, to the two categories. But assuming this, any potential W on X will define a natural object in this categorified cotangent bundle supported on its graph. And the home in the two category between the object associated with the zero section and the object associated with to this to the the potential is going to be the matrix factorization category, which is, that's how Kapustin outlined the definition of the category, or Kapustin-Rozansky maybe, by saying take two smooth Lagrangian, then locally if they intersect at only one point, you can make one as the graph of the potential on the other, and that's the home. So that was a starting point. Of course, there should be a definition and there should be a computation. Again, this is formally means this is true at the formal level. That's the only level I know. All right, but now we can address the mystery, which wasn't really a mystery, of the problem of restricting potential to submanifolds. So, even if the potential from X to C has no critical points meeting, say, a closed submanifold S, the graph of its differential will still intersect the conormal bundle to S in X precisely over the critical points. And the home categories between the two in the Shukrut-Garni are the matrix factorization exactly of S, of the object associated with the conormal bundle of S and the potential. Of the structure sheaf of S and the potential on S. So home computed between the conormal bundle and the graph end up being home the matrix factorization on X by some natural coordinate argument, at least if the intersection points are isolated. I don't think I understand the general setting. So why did I suddenly decide to take the conormal bundle? Well, that's actually, I probably do say it later, but I should have said that now. If you have a holomorphic map between manifolds, you induce a functor between the Shukrut-Garnis of the cotangent bundles simply because the differential of the map is a holomorphic Lagrangian in the product of the cotangent bundles. That gives a correspondence much like in Floer theory. And assuming that some minimal finiteness condition on the category, that actually defines a functor. It's more like a bimodule actually. All right. So now let's just revisit the story for torus fixed points. So if you start with the linear category with locally trivialized torus action, what you're going to get from it is a formal germ along the zero section of an object in this Shukrut-Garni theory. By the way, the formal germ of this Shukrut-Garni theory is well defined because it just requires formal deformation theory, so that we know. What's not clear is that you can actually extend it to something living over the cotangent bundle. So the underlying category now is recovered as home in this Shukrut-Garni of the zero section with the object C hat. And you should think of this as the analog as home over the group from the regular representation to C. That's C again. Home from the regular representation to another representation recovers the representation. So a zero section is a regular representation. The category of coherent sheaves on T check is a regular representation. The fixed point category instead is the intersection with the vertical fiber at 1 of the cotangent bundle. And that's home from a trivial representation. But this suggests that you actually have to make things more precise. So for things to be well behaved, you want this formal germ to be enhanced to reasonably finite object in the categorified cotangent bundle. So at least something with proper support. So you would need to have a delocalization of this Lagrangian germ or of this object constructed from the category. And interestingly enough, in examples, we do get that. So a mirror of the Fukaya category C will in many known cases have the form of a complex manifold, the potential, the holomorphic map from Y to the torus. And the graph of d phi inside the cotangent bundle of Y times that of the torus gives a functor from the between categorified cotangent bundles. And the properness that would guarantee that our object is finite seems to be the properness of a critical locus of, that's W, over T check. Or that implies certainly properness of the support. Lagrangian. In fact, what you're going to get is you look at the critical locus of W and you consider a new potential on T check. A multi-valued potential consists of the values of the W at its critical loci, at the components of a critical locus. And I'd like to close, probably a bit early, by explaining what happens in an abelian case. So here's the theorem of Bezrukavnikov, Finkelberg, and Merkovich. G is a reductive connected group, and G check the Langlands dual group, and omega G the base loop group. Then they give a geometric interpretation of this ring, the equivariant homology of omega G, where G acts by conjugation here. Adduction. Namely, it's a holomorphic GIT quotient, holomorphic symplectic GIT quotient of the regular part of the cotangent bundle on G check by the conjugation action of G check. So regular means, well, the fibers of T star can be identified with vectors in the Lie algebra, and you throw away those which are singular. So throw away something before taking the quotient, and actually, as people know in GIT, that tends to make the quotient bigger because there's a bit less collapsing, crushing going on. So instead of being something like the cotangent bundle of T check divided by the Weil group, it's actually a blow up, a partial blow up of that. Namely, you just take this variety, take its functions, and adjoin these ratios of functions e to the alpha minus 1 divided by alpha. So this is a function on G check, this is a function on G check star on the fiber. So this is a function on the base on G check, this is a function on the cotangent fibers. You adjoin those. So that forces you to blow up some walls of the Weil chambers. And here's an example to understand a bit what we're talking about. That's the example where G was SL2, so G check was PSL2. And what we're going to get, it is a surface actually. It projects on one hand to T check mod W, that's also an affine line in this case. And also the Lie algebra mod W, also an affine line. And it's not the product, it differs from it by the fact that we've blown up the identity in the torus. The pink fiber is the exceptional fiber, and then we've thrown away the proper transform of the zero section. So the exceptional fiber, in general, it's the most exceptional locus and high.
Just go to that last bit again. Just say again what it was. So we started with what was the original thing?
So the original thing would be the product of A1 cross A1 actually. Okay. You blow up the origin, and then you remove the proper transform of one of the axes. And the axis in question is what used to be a zero section of the cotangent bundle. But the place where I'm lying is because where am I lying? I'm sorry. Shh. I'm sorry, I lied. I goofed up and lied. I didn't clean. Let me say it correctly again. What you take is A1 cross A1. Then you mod out by Z mod 2 with a sign on both. So it has a singularity. Now you blow up the origin and now remove the proper transform of the zero section. And actually it's not A1 cross A1, it'd be A1 cross C star, but after the modding out by Z mod 2, that becomes an affine line. C star mod Z mod 2, sorry. So I'm sorry, I rushed and I said it incorrectly. In fact, this manifold has a teeny bit of topology. It has non-trivial double cover. So the projection, the two copies of A1 drawn here is not 1-to-1, I think it's 2-to-1. Because I've sort of modded out by Z mod 2 in each factor on these sides. So whereas you mod out only once by Z mod 2. Where's the Weil group? Only once by the Weil group. It has a double cover, which would be the construction for G hat is SL2, which would correspond to the group being PSL2. And then there will be another blown up point, another copy of this thing. So the most exceptional locus, in this case only one, is what will play the role now of the zero section in the torus, and the functions on it are the equivariant homology of the based loop group of G. This vertical line here comes from the unit fiber in the cotangent bundle that plays the same role. So this will play the role of a trivial representation, this will be the regular representation, and the potential that you get, I mean, you will have a graph somewhere here. So if you want to compute the fixed point category, you would have to take the intersections with the unit fiber. What I've drawn here in blue actually is a Hamiltonian displacement of this vertical fiber under the quadratic Casimir. It's a quadratic function coming from the projection of the Lie algebra, and that plays a role in when you consider theta polarization in gauge-Romov-Witten theory, and I'll mention that next time, but not today. So the claim in this case is that defining a locally trivial G action on a category C is the same as making it an object supported near the pink section, the exceptional section, an object in the categorification of this holomorphic symplectic manifold. And good behavior of the gauge theory requires you to have a global object. So notice, if you have such an object, the underlying category is always supported on the zero section. So in other words, I'm saying that for the gauge theory to be well behaved, you must have a lot more information than just the original category. The original category would be read off just by looking here, in the formal neighborhood, in fact. If you want just a 1 second justification of it, it's because I had mentioned that locally trivial T actions on C were in correspondence to ring homomorphisms from the group ring of pi 1 of T to the Hochschild homology of C. And there's a similar statement for locally trivial G actions. They correspond to E2 ring homomorphisms from chains on the based loop group of G to HH star of C. And this as a ring is isomorphic to its homology, and is a polynomial ring if G is simple or semi-simple. So somehow this pink thing here is replacing the torus because it's spec of the ring that's supposed to, over which the category is supposed to fiber, over this pink thing. Right. But what these chaps provide is they provide an uncompletion. So a priori, I mean, homotopy theory would tell you should look at the formal neighborhood of this pink thing. What these chaps provide is an uncompletion of the formal neighborhood to an actual manifold. And the computations I did in non-abelian gauged theory show that this is the correct uncompletion, meaning you do need intersection points far from the zero section to compute the correct field theory, and you can also rule out other obvious candidates. For example, you could try the cotangent bundle of this pink thing. That's not right. It gives the wrong answer as well. I mean, I can prove that this is equivalent to, well, this is the picture which computes the fixed point categories modulo the same gap which exists in the definition of the categorification. There's a place where I would need a local computation, I can only do a formal computation. So as far as definition allows, we can think that this is checked, that this is correct. But since this hasn't really been defined yet, I can't claim, I can prove a statement involving this exact space. Again, homotopy theory just allows you to see the formal neighborhood of the pink line. And I'll stop early for a change.
Any more questions?
Yes. Just see if I understand sort of the broad picture. So you're trying to study what I would have initially thought of as being a two-dimensional.
That's right.
Theory, right?
Yeah.
We have some particular one. So the way you describe it, you say you have a particular category with a group action.
Yeah.
You look at some corresponding gauge theory in sort of two-dimensional. But now you're saying that it's for some reason better to think of that as being living on kind of a wall that's the boundary of a three-dimensional field theory?
Yeah, you could say it that way. Because let's put it this way. Boundary conditions for the trivial three-dimensional field theory are two-dimensional TQFTs, right? So these boundary conditions for the trivial gauge three-dimensional TQFT are two-dimensional gauge TQFTs, yes.
So
that's a way to say it.
Saying it in those terms, is it possible to understand why this helps? I mean,
why this? No, if you state it in those terms, it doesn't help because I don't think I understand the gauge two-dimensional theory. In fact, on the contrary, this seems to give a model for it. But the reason it helps is because maybe it's coming back a bit to your question about B and A. So when you define a locally trivial G action, so for a torus, a lot of things are fairly clean and crisp because there is no derived information coming in. When you go to a non-abelian group, to have a good notion of locally trivial G action involves the notion of homotopy trivialization. Now, that means passing to homotopies. These things are very tricky. You can make things homotopy equivalent with various constraints and get different categories as a result. In fact, there's an obvious way, the obvious way I suggested here, to define B model action, right here actually, to define an A model action of a group on a category just by saying this. And from there you can go on to compute by, let's say, standard techniques, a fixed point category, and you then go to the question that I forgot if Tim Perut or somebody asked in the first lecture. If you take this answer and start computing invariance, do you get the invariance in the gauge theory? And the answer is no. Somehow this local triviality of the action is very tricky to implement without loss of information. So what this picture does, this mirror picture lens the holomorphic world, gives you a rigid model on which you can compute things that give the correct answer. For example, on Thursday I'll probably go review Witten's Young-Mills computational theory, and we'll see that we have to count exactly the intersection points up here, none of which are in the neighborhood of the pink line, which is what formal homotopy theory or computation would predict. So one needs a more... The A side is bad in the sense that it's not obvious. You need to rigidify it in some way, and it's not obvious how. And this gives you a rigidification. And that's also why I didn't study so much the B to A picture, because it's going from something that's already very rigid and crisp to something that's sort of soft and imprecise. So aesthetically it'd be interesting, but there would be no benefits from it. This allows you to compute and get the correct answer. Whereas the homotopical definition just allows you to compute. Okay.
Okay, let's thank Konstantin again.